All right, temperature. What a fickle thing. We can never seem to agree on the thermostat. It's 3 degrees up, 3 degrees down. It shouldn't really make a difference. It makes a difference for some of us that may have trouble sleeping. Now, what the heck is going on? Now, again, the interesting thing is number of systems often involved using 0 as the freezing point of water. Celsius basically, more or less still does that. Maybe off by like 0.4 degrees or something like that. Maybe that was boiling for water. Essentially, for a deeper dive into thermodynamics, please see Stephen Wolfram's blog over here. All right. So early times or early attempts to quantify temperature. You go back to Philo of Byzantium. He designed a hollow sphere just filled with air and water connected to an open air picture as a rudimentary thermometer. What happens? Temperature goes up. It's going to increase pressure. So, as a reference, you may have, maybe not more recently, but at least when I grew up, we had those little mercury thermometers. So, mercury, hopefully it was sealed well, but behind the glass, but you have a glass thermometer. You put it under your tongue. The temperature of mercury goes up. Oh, look, you're going to have your temperature. And the sheer fact that we did that, potential heavy metal poisoning aside, it seemed to work remarkably well. So it was the same principle there. Okay. So we had a bunch of other methods there, and you had in 1702, Gualmi Amamatons. I completely butchered that. I apologize. I don't speak French. Predicting the minimum temperature of minus 240 degrees Celsius. Anders Celsius in the 1700s originally developed this, and he developed it in kind of an inverted scale, and we kind of just used the flip version of it. And that's where we get the unit Celsius from. So we got better technology and everything. Newton started proposing different things, which was, it's kind of dubious here because Newton proposed 0 degrees to be the freezing point of water and 12 degrees to be the temperature of a healthy human. It's like, it's the 98.6 degrees is generally what's commonly accepted here. And again, some of us run a little bit hotter, a little bit cooler. A little bit of a differentiation here. But it was Lord Kelvin, whom is the namesake of the Kelvin, wrote about it on an absolute thermodynamic scale to first calculate the minimum temperature of negative 273 degrees Celsius. In 1954, the General Conference on Weights and Measures adopted the Kelvin as the base unit for temperature, setting a reference point of 273.16 as the triple point of water, the point where water exists as a solid, liquid, gas, in thermal equilibrium. Okay, even water is again popping up. Is there nothing it can't do? All right, the Kelvin, to our current definition, is the symbol big K, is the SI unit of thermodynamic temperature. It's defined by taking the fixed numerical value of the Boltzmann's constant, K, to be 1.38649 times 10 to the minus 23 when expressed in the units of JK. Just kidding, it's joules divided by kelvins, or energy divided by temperature. As we saw on the board, that's literally what it was. It ends up being technically the Planck energy divided by the Planck temperature. All right. But our modern definition, as we can see here, we're just kind of doing the same thing. We have 1 Kelvin as defined by the numerical value of Boltzmann's constant, divided by the numerical value of Planck's constant, as well as the numerical value of the transition frequency of cesium. Then we invert everything, and we then multiply by the transition frequency of cesium, Planck's constant, and then we divide by Boltzmann's constant. So we're taking the numerical values of the constants, Then we multiply by the actual constants inverted. Gives us this number here, and then we get out 1 Kelvin. So as we can see, we've got all that jazz here. We've got numerical value, Boltzmann's constant, numerical value, Planck's constant, numerical value of Cesian transition, times all that jazz, and we simplify, we get 1 Kelvin. Great.